So last time I defined the category for you and explained the most important features of a category: composability and identity. Okay, and I started talking about the most important example of a category that we use in programming. That's the category of types and functions, right? So in programming we have types and functions, but the model for types and functions is really sets and functions between sets, right? So I mean, every time you design a language, you have to provide semantics for the language, right? What does it mean, a certain thing in the language? And a lot of languages are defined using so-called operational semantics. I mean, the ones who actually have semantics, right? There are very few of them, none of the major ones. But they sort of, like, parts of it have semantics defined, right? And there are two ways of defining semantics. One is by telling how this thing executes, right? So that's called operational semantics, because you're defining operations of the language. You know, how one expression or statement can be transformed into another simpler one, and so on. And the other is called denominational semantics, where you actually map it into some other area that you understand. And in particular, the most interesting way of mapping is into mathematics, right? So you build a mathematical model and you say, this statement in the language or this construct in the language corresponds to some mathematical thing. And this mathematical thing, for instance, for types, is a set of values. For functions, it's a function between sets. Okay, that's why it's so important, and that's why I will just talk about types sometimes, and sometimes I will say set, sometimes I will say type, because I have this semantics in mind. Okay. So what is important is that a function in programming, especially when you are considering, imperative programming, it's not exactly the same as a function in mathematics, right? So we have to be more specific. By function between sets, we really understand something that in programming would be called a pure function, right? And it will be a pure function and a total function. Because a mathematical function is defined for every argument, not just for some arguments, right? This is like the major source of problems in programming, that we have these partial functions that are defined for some arguments, and for other arguments they explode, right? I mean, if they throw exception, then we catch this exception, that's fine, right? But quite often they don't. They just destroy the computer, right? Explode the monitor. So a total function is defined for all its arguments, right? And these arguments are taken from some type. So like it's a function on integers, it has to be defined for all integers, right? And it's a pure function. And how can you tell if a function is pure? So I have this test for a purity of a function. A function is pure if you can memorize it, which means you can turn it into a lookup table, right? Because for every value of an argument, it should return one particular value, right? And you can just remember this value, okay? You call this function once, it evaluates it, and then you can remember it, and next time you do a lookup into a table, right? So you have types that are finite, that only have a finite number of elements, like Boolean, right? Then it's really easy to tabulate them. Functions on characters, if it's just ASCII characters, are really easy to tabulate, right? All of these functions, like is alpha, or is printable, they are all actually tabulated, so they are very fast. Now functions on let's say, integers or strings, they usually cannot be tabulated, right? But that's only a problem because of resources, right? I mean, if we had infinite resources, we could tabulate them. So ask yourself the question: can I actually memorize this function? And for instance, a function like getChar cannot be memoized, right? You call it once and you remember, oh, it returned h. Good. I'm just remembering this, and from now on, whenever somebody calls function getChar, I will return h. Okay, and that's it. No, you can't do this, right? So this is not a pure function. Now, of course, you might say, okay, but you know, how can you program using only pure functions, right? We need things like side effects. We need, okay. So all this stuff can be described on top of pure functions. But what we really want is get to the bottom of the abstraction. Like, what is the lowest level or the highest level of abstraction? I don't know, depending how you look at it, right? I mean, so what is the atom? What are the building blocks? What are the simplest building blocks from which we can build more complex stuff, right? Using, again, the same idea of composability. So first we want to decompose the problem, get to the little blocks at the bottom, and then recompose stuff from there. So when we are decomposing this idea of using procedures and data types and so on, we eventually get to the bottom, and that's pure functions. So on top of pure functions, we can be building more complex stuff, including things like I/O. So now that we have this category of types and functions, right? And I talked a little bit about this. Now let me expand on functions. Because functions are very interesting. There's much more to know about functions that we usually consider, right? So they're really interesting beasts. Even these pure functions, right? Total pure functions. We have to look at them from a slightly different perspective, from a perspective of how we can use them as morphisms in our category, right? Category set. Which contains sets and functions between sets. So, functions are defined in mathematics as special kinds of relations. Okay? What's a relation? Relation is, you take two sets, they have elements, right? And now we are talking about sets as in set theory, not as a category. So in a category, we won't be able to look at elements, but in set theory, we look at elements, right? And a relation is just a subset of pairs of elements, okay? So this is okay, maybe somewhere else, right? So it goes somewhere else here, goes somewhere else, okay? So so it's just pairing of things. We say, oh, this element is in a relation with this element, okay? And again, as I explained, we are using our brains to understand these things, and here we are like talking about relationships. So this is our relationship brain talking about social interactions in mathematics. Okay? Yes, you had a question?
Does the relation have to be total?
Does the relation have to be total? In general?
Yeah.
No. We're just talking about general relation in mathematics, right? So we say, okay, this person is in a relation with this person. They are, let's say, friends. Okay, so this guy is a friend of this guy. Maybe this guy is not a friend of this guy. So the relation doesn't have to be symmetric, you know. No. So let me define a relation, okay? First of all, what is a set of pairs? A set of pairs is in mathematics is called a Cartesian product, right? So we have two sets, S1 and S2, right? And we can do a Cartesian product of it. So all elements from one set were paired with all possible elements from the other set. So the set of all pairs forms the Cartesian product. Now we take a subset of this Cartesian product. We just pick some pairs randomly or not. You know, that's like if they are meaningful. Then we just pick a subset, and any subset of this Cartesian product is a relation. By definition, that's a relation. Okay? So there are no other requirements. Just a subset of the Cartesian product. That's a relation. Okay? So in this sense, relation does not have directionality, right? Whereas functions have direction. Functions are these arrows, right? So this is one of the most important things to understand, that functions have some kind of directionality. So what kind of condition do we have to impose on a relation for it to become a function? And in a relation, we can like have this element, pick element in this set. It can be in relation with many elements in this other set, right? And vice versa. An element from this set can be in relation. Well, okay, I'm putting these arrows in this direction. Okay. So many elements from set S1 can be in relation with a single element in set 2, or one element from set 1 can be in relation with many elements from set 2. Both are okay for a relation. One of them is not okay for functions. Okay? I need an eraser. I'm not gonna use my hand. Which one is bad for a function? The top one, right? One element, one argument of a function cannot be mapped into a bunch of things. It has to be mapped into one thing. Okay? It's still okay for multiple arguments to be mapped into the same value for a function, but not the other way. So that's where the directionality comes from. Plus, we want to be considering total functions for our category, right? So this whole set has to be mapped. All elements of this set must be mapped into something in this other set. Okay? However, it's not true that all the elements from this set have to have have to come from this set. So this could be a subset that's being mapped. Okay? Now these things have names, so let me name these things for future reference so that we can talk about them easily. So if you have a function f, okay, so this is like a graph of this function f, this is called the domain of a function, right? The domain of the function is just this set from which we are starting, the whole set. That's its domain. This set is called the codomain. And this subset that was obtained by mapping the whole domain is usually called the image of the function. Okay? So functions are not symmetric in this way. You see? This is the whole set. This could be a subset. Multiple elements can be merged into one element, but not vice versa. Right? So there is this directionality. And this directionality is very important. That's a very important intuition about functions. And this is not only an intuition about functions, because later we'll see that in category theory we have all kinds of other mappings. We have mappings between categories called functors. We have mappings between functors, which are called natural transformations, and so on. All these mappings have the same kind of directionality. Okay? And the simplest way to understand this directionality is asking, is the function invertible? Like, if I go from here to here, is it possible to go back? Right? And usually, it's not. So if there is a function f from some a to b, you know, there isn't always a function that goes the other way around that is the inverse of this function, right? How do we define an inverse of a function? Well, it has to, so if you have a function that goes from a to b, and I will be using this notation that's just taken from Haskell, okay? So f is a function, double column means this is the type of function. The type of function goes from A to B, right? So this is set A, this is set B, or type A, type B, okay? So this function is invertible if there is another function that goes in the other direction, from B to A, okay? That's the inverse of this one. What does it mean? It means that G after F equals ID. Okay? So if you first go F to B and then go back from B to A using G, you should end up in the same, exactly the same point. So if you have an X here, right, F maps it into some Y here, and then you apply G to Y, you should get back to X. Okay? That means the inverse. Okay, but we can compose them two ways, right? So G after F is 1, but there's also a composition F after G. And this one also has to be an identity. So we go G first, and then F, and you should end up in the same point. Okay? So this makes it symmetric. So a function that's invertible is automatically symmetric. Okay? And a function that's invertible is called isomorphism. So this is the definition of isomorphism. And notice an interesting thing. This is in the language of categories, okay? Maybe with a little bit of additional notation. If F goes from A to B and G goes from B to A, then this is an identity in which object? In A, right? So now let's forget about this picture and say A, B, this is F, this is G. Okay? So G after F, F, G, I'll get identity on A. And then F after G, so G first, F next, it's the same as identity on B. Okay? And I have written this in categorical language. I'm not talking anymore about elements. Right? Here I was talking about elements of sets. I don't need to. Okay? Now I can go back to category and say, this is a definition of isomorphism in any category. Not only in category of sets, in any category. Because it's expressed in terms of composition and identity, nothing else. Right? So F is an isomorphism if there exists a G with these properties. Okay? Okay, but so isomorphisms are great because isomorphisms like identify two sets. They say this set really looks like this set. There is like one-to-one mapping between elements of these sets, right? So that's you know, if this is a two-element set and this is a two-element set, you know, I have a mapping between these elements. That's great, right? For my purposes, they are sort of like identical, right? I mean, it's not really identity, it's isomorphism. But I have an identification between these two sets. So for finite sets, you know, an isomorphism is just an identification of elements. This element corresponds to this element corresponds to this, and so on. One-to-one correspondence. For infinite sets, of course, this is a little bit more complicated. For instance, you can have a one-to-one correspondence between natural numbers and even numbers, right? Like y equals 2x, even numbers, right? Or odd numbers, 2x plus 1, right? These are functions that are invertible. Is that true? No. No. But if this is a set of even numbers, right? So let's say this is a set of even numbers. Not the set of all numbers, just a set of even numbers. And this is the set of all numbers, n, right? Then I have one-to-one correspondence between even numbers and whole numbers, right? That's because they are infinite, and for infinite sets you can do tricks like these. But if this is a natural numbers and this is, let's say, you know, real numbers, let's say, right? Real numbers. Then you know that there is no correspondence like this, right? Do you know that? Yeah. Okay. There's a good argument that they are not. But that's just a side remark, right? So it just to make you aware of the fact that isomorphisms kind of tell you that these two things are, for some intents and purposes, identical, right? But there are most functions are not isomorphisms. Right? Most in the sense of, I don't know, what does it mean most, but like most functions that we deal with are not isomorphisms. And there are two reasons for a function not to be an isomorphism. Okay? So you have to have good reasons not to be an isomorphism. One reason is because a function can collapse elements of a set, right? So it takes multiple elements of this set are mapped into a single element of this set. So let me be sort of more precise here in this drawing and just focus on one thing. So you have some x1 and you have some x2, and function f maps both of these elements into the same y. Okay? For instance, let's see, a function is even, which returns a Boolean, right? So is even maps every even number into this one element of the Boolean called true. All even numbers are mapped to true. All odd numbers are mapped to false. So lots of numbers are mapped into one body, right? So we have this kind of gluing going on. So that's one reason for this function not to be invertible. There's another reason for a function not to be invertible, and that's that it that its image does not fill the whole codomain, right? So you have a function in which so this is the codomain. There are some points here. This is the image, right? The image of function f. There are some functions outside of the image that just don't correspond to any x's here, right? So if you would want to invert this function, you would have to create a function g, and what's the value of g on this point, right? Maybe you can invert it for these points, and you can say, okay, this x is mapped to this y. Okay, maybe I can invert it. If I don't have this gluing, right, then maybe I can invert it. But I don't know what to do with this guy. What should g be on this? No idea. Yes?
Isn't it possible to have an inverse relation in this case though? Or do we not care about those? Like, for instance,
Yes. And then in fact, at some point people have this, instead of inverting functions, what you could say is that the counter image of this y, right, it will, okay, in this case, right, it will be some bunch of points here, right? And this bunch of points that are mapped to the same point, it's called a fiber. Okay? And fibration is a very interesting topic in category theory. Okay? Because then you can build a set of fibers here and you can say, okay, on a set of fiber, this thing is invertible. Right? I'm getting really ahead now. Okay? So there are these two reasons for non-invertibility. So I like to think of this like a function. If you think of a function as something directional, a process that takes place in time, a function that's not invertible is something that increases entropy, right? It boils an egg, and you cannot unboil an egg, right? So this kind of things make make this thing non-invertible. And it's very important because these two things, these two phenomena here that make it non-invertible, they correspond to a very interesting thought process that we use to solve problems. This corresponds to abstraction. This means, I really don't care which of these points I came from. I'm only interested in one property there. So I'm abstracting. I'm throwing away some information about whether it was x1 or x2. And I'm left with just one piece of information. For instance, I'm throwing in information about what was the exact number that I mapped. I'm just extracting the information whether it was even or odd. Okay? So I'm sifting information, right? And I cannot invert it. I cannot say, oh, it was an even number, so it must be 2. No. It must be 0. No. Right? I don't know how I came to this conclusion. But I have abstracted a bunch of information. And now I have just this one piece of information that I care about. Okay? So this is the process of abstraction. This, on the other hand, is the process of modeling. Okay? I'm modeling this set inside this bigger set. Or maybe it's not bigger, right? But since it has this environment, right? So I'm saying, okay, I'm recognizing the pattern that's defined by this set inside the second set. Okay? So I'm mapping it. So I'm sort of like injecting this guy here. Right? This is some, stick figure or something. And I see the same stick figure here. Okay? So, you know, this is maybe a human sitting in a cave, right? And this is the shadow on the wall of the cave, right? I'm embedding it in here, okay? And I'm abstracting maybe also, right? Because this is a three-dimensional guy, this is a two-dimensional shadow and doesn't have an, you know. So I'm doing both abstraction and modeling. And now somebody comes and recognizes this. Hey, you just draw a person. Oh, right? The first human being drew a person on the wall and they're so excited. Right? So they just discovered category theory. Okay, so mathematicians, of course, have names for these things, right? But their names are like the inverse of what I described. So, like they say, okay, if a function does not collapse things, then if it's not collapsing, then it's called injective or injection. Injective function does not collapse things, okay? So if you have two different x's, x1 and x2, and you map them with the function, then you will always get y1 and y2. They will be different. So if x1 is different from x2, then okay, let me write fx1 and fx2, right? So if these guys are different, then these guys are different too. Which means it's not collapsing anything, right? It's just injecting the thing as is, right? The whole thing with all the points in here get transported to this other set, okay? No shrinking, no forgetting, no abstraction, right? So that's an injective function. It just injects this thing. And this thing, also, they have a name for the opposite of this, namely, if the function covers the whole codomain, right? If the image is equal to the codomain, then it's called surjective. And that's from I don't know, French or Latin. Sur means on, right? So it's onto. It's a function that's onto the other. So this one is a counterexample for a surjection, right? That's not a surjection because it has this terra incognita here. A surjection doesn't have this. Surjection covers the whole thing, right? And in particular, in set theory, you know, if you have a function that's both injective and surjective at the same time, it's actually an isomorphism. You can invert it, okay? So that's a good thing to know. But now you might say, okay, so we know something about set theory, that there are injective functions and surjective functions. Now, if we define this in terms of elements, right? I said elements here, right? And surjective, it means that so this, like for all y's in the second set, y equals f of x, right? There exists an x. For all y's there exists an x, that y is equal to f of x. Okay, that's in terms of elements of the sets. So like, there is no thing outside. Every element that I pick in this set has a counter image. Okay? So I have defined something in terms of elements. And now if I go to category theory, you know, the set category, how do I talk about injections and surjections, right? If I cannot look at elements. Turns out, I can. But it's a tricky business. Because I have to express this stuff now only in terms of morphisms, right? Of other morphisms. So I have to turns out I have to talk about all the other objects in the category, all of them, in order to define this one property. Okay? And this is very, very characteristic to category theory. That if you want to define a property of an object or an arrow, you define it with respect to essentially everything else. Okay? It's like this is a very holistic approach, right? You cannot just focus on one little thing, because no matter how good your microscope is, you cannot look inside this little point, right? This point where A is, right? And here's B. Because in category theory, this is a point. Here, it's a big thing. I can look at using a microscope. So if my microscopes don't work, maybe my telescopes will work. Okay? I'll be looking at the whole universe, and I will say, okay, this little guy is in a relationship with the universe, and the relationship of this guy with the universe is such that I can say something of this type, like it's sort of like injective or surjective. Except that in category theory, we don't like Latin, okay? We use Greek. So instead of saying something is surjective, you know, onto in Greek is epi, right? So we'll say that something is surjective, it's called epic, okay? And something that's like injective, it's called monic. Or monomorphism, right? Monic thingy or monomorphism. Monomorphism. And this can be called epimorphism. Oh, I'm getting outside of my area. Epimorphism. Or an epimorphism. Okay? So, epimorphism and surjective function. It's the same thing when you consider just set theory, right? And injective and monic is the same in set theory. But these things are defined for any category. So they are much more general. So how would we define this stuff? Okay, let me erase this, maybe. You remember this? That's an easy thing. Okay? So how would we define, let's say, an epimorphism? I think that's easier. An epimorphism. So we have a function from A to B. Sorry, not a function, a morphism. Okay, but let's first think about the function. But let's try to like define this property of a function that's surjective in such a way that we don't talk about elements. Okay? So first we'll start with a set, but we'll try to find the property of a surjective function that can be expressed purely in terms of other functions. Okay? So let's first think about if it's not surjective, what does it mean? If it's not surjective, it means that there are guys here that are not in the image, right? So suppose that I take another function called G from this set. So this is my set A, this is my set B. Let's say I pick a set C, whatever set, right? And the function G from B to C. So as you can see, function G will have values for elements that are in this terra incognita, but also for these elements that are in the image of F, right? But if I compose these two, and here's the trick, I have to talk about composition, because composition is the only thing I have at my disposal in a category. So I better talk in terms of composition, right? So if I talk in terms of composition, if I compose this function f with g, then look what happens. This x will go inside the image, and g will take it to some, so this is, let's say, y, this is some z, right? Okay? So g after f will actually not probe this terra incognita, right? Even though g maps everything, inside the composition, it will actually only act on this, right? Inside the composition. Because it's acting on y's, and these y's were obtained by acting on x's using f. Right? That's how composition of functions is defined in set. Aha! So, if I take two such functions, g1, let's say, and another function, g2, and these functions only differ here. So g1 maps this guy into this point, and g2 maps this guy into this point. Then g1 is different from g2, right? Because they map points differently. Or actually what I want to say is the same point is mapped by g1 and g2 to something different, right? That's the difference. The same point is mapped to two different points. That means g1 and g2 are different functions. But if they only differ outside in this halo, then the composition with f will be the same, right? So the composition g after f, g1 after f, will be the same as g2 after f, even though g1 is different from g2. So the converse of this is, if for every g1 and g2, if g1 of f equals g2 after f, follows that g1 is equal to g2, if for every such combination, then I can say this function is surjective, right? I'm just like reversing the logic. If for any object C and any pair of functions, g1 and g2, from B to C, if g1 after f is the same as g2 after f, then g1 must be equal to g2. If this is true, then the function is surjective. And look what happened. Now I have expressed this purely in terms of categorical terms, right? And maybe I should put one more for every C, right? For all C's, for all objects C's, for all morphisms G1, G2 that go from B to C, okay? If from G1F equals G2F follows that G1 is equal to G2, then this is an epimorphism. And this definition will work for any category. In the category of sets, this is just exactly the same as a surjective function, right? But in any category, I can define something like this, because I'm only using composition. But notice that I'm using these quantifiers for all. So I have to consider all objects in my category, all C's, and all possible pairs of morphisms from B to C, right? So I'm really, really looking at the whole universe just to define this one property of F, okay? And the way to remember this property, one way of looking at this, is that if I have this kind of relation, it means that I can do, I can cancel something on the right. It means if I have G1 after F equals G2 after F, that I can cancel F. And what do I get? G1 equals G2, right? This is actually a good point for a break. Yes? Yes. Okay. Let's take a break.